Okay, so let's get going. So my name's Mark Allen. I'm an astronomer working at the Strasbourg Astronomical Data Center, the CDS in Strasbourg, and I have the pleasure of being the work package leader of work package 4 of the ESCAPE project. We'd like to welcome you to this webinar today. We've got a bunch of talks that help to explain the work that we're doing as one of the work packages in the ESCAPE project and how that's integrated across the different work packages and how it's related to sharing data in astronomy and to the development of the European Open Science Cloud. I'm aware that we have a diverse range of people in the audience, and so we try and do our best to make sure that the presentations are understandable to the wider audience, but of course we're going to dive deep on some of the topics, and there might be a few acronyms and lead to questions at the end. Nevertheless, I hope that we give you a good overview of that. We have a program which has a number of talks. I'm going to give a kind of introduction, and then there'll be some more details about what we call the Virtual Observatory in astronomy and some implementation examples from the large infrastructure, the ESFRI and research infrastructure partners that we have in ESCAPE. And at the end, we'll wrap it up and have a Q&A as well. I would encourage you to put your questions into the chat. We'll try and grab those, and there'll be an interactive discussion at the end. So welcome everybody. I'm going to launch straight into a presentation. So I'm going to share my screen. I'm going to share my screen. It's going to happen just a second. Okay. Okay, here we go. So in this introductory presentation, sorry. Right. In this introductory presentation, I'm going to talk to you about what we call the Virtual Observatory in the ESCAPE project and in the EOSC. So that's already a lot of acronyms. The ESCAPE project is the European Science Cluster of Astronomy and Particle Physics, ESFRI, research infrastructures. It's one of the cluster projects related to the European Open Science Cloud that's funded in Horizon 2020. So I put a picture straight up so that I can explain what I'm talking about. The Virtual Observatory, it's a framework built on common interoperability standards for the access and use of astronomy data. You can publish your data to the Virtual Observatory. You can use virtual observatory tools to access the data and to do your science. Here's just a couple of visual examples of that, where the data that you see in this application here, just one of the applications that can access the Virtual Observatory, it can get data from what we call the registry. It's a bit like an EOSC catalog. You can get data from many observatories and missions. There are thousands of all-sky data sets, and even some of the very largest catalogs and surveys with billions of sources, even some just published in the last couple of weeks about the Gaia satellite. It's a sort of virtual research environment where you can access it in different ways. The animation on the side there is showing through a Jupyter notebook and the way that you can interoperate between different applications. So the Virtual Observatory is a way of making data fair, where fair is findable, accessible, interoperable, reusable, as we talk about in open science. It's an operational framework, it's global, and it's mainly focused on astronomy data and services. Astronomy has been this kind of pioneer of fair data sharing. It's an existing framework. It's populated by some of the major data providers like NASA and ESA, many data centers. It's built on something called the International Virtual Observatory Alliance, IVOA, which is an organization that defines standards for interoperability. And that's been going for some time, since about 2001. And it's one of the things that's recognized in the roadmap of the large infrastructures in Europe, the ESFRI, on the ESFRI roadmap, its most recent version, which has just come out. in 2022, built together in 2021 as a example of a global implementation of a fair disciplinary framework. And it's also in the terms of the European Open Science Cloud, it's one of the examples that's quoted in the SRIA document, which stands for the Strategic Research and Innovation Agenda. These activities about making data fair through the Virtual Observatory have been going in practice for a number of years and supported by what we call the European Virtual Observatory projects, with partners contributing those projects over a number of years. And the disciplinary roadmap for astronomy, which is called AstroNet, has also integrated in the priority of the Virtual Observatory since its first version in 2008, its update in 2014, and the current update in 2022. So in ESCAPE, which is a large project with many partners and many work packages, the Virtual Observatory is supported by the work package 4 that we call CIVO, and that is about connecting the ESFRI projects to the EOSC using the Virtual Observatory framework. So those acronyms, EOSC is the European Open Science Cloud, and when we talk about VO, we're talking about the Virtual Astronomical Observatory. And then part of ESCAPE, you see we have the sort of thematic cell, as we call it, of ESCAPE, which corresponds to all of the work that happens in ESCAPE, including the software repository, a development called the data lake, a science platform framework, as well as activities to do with citizen science. So the Virtual Observatory is the part which makes the standards that allow the ESFRI partners and other data providers to connect to the Virtual Observatory, to use those tools and to do their science, as well as the connection of the Virtual Observatory itself to the European Open Science Cloud. And the approach that we've taken in ESCAPE in this work package has been to combine partners that come from these large infrastructures, from ESO, the European Southern Observatory, from the Square associated partners such as Astron, other radio astronomy activities like the Joint Institute for VLBI. There are also other high energy physics experiments, observatories such as the Cherenkov Telescope Array. We also cover EGO, which is Gravitational Wave Observatory in Europe, and also solar physics related to the European Solar Telescope. So we combine those partners with partners from the CNRS, from Italy, from the University of Edinburgh, from Heidelberg, from Spain, who have experience with the European Virtual Observatory and experience with making standards and sharing data. And we bring those different sorts of partners together. And the approach then is to integrate that VO data and services into EOSC. We've gone the path of working with the EUDAT project to get the Virtual Observatory Registry into the what's called B2Find as a stepping stone towards the EOSC catalog. And then most of the activity is about the standards and making sure that we build standards and we implement standards based on the priorities of those large infrastructures. We do that with that partnership I just talked about, but also with community training events for scientists, but not only, also for data providers and the producers of the data. There are a couple of special activities that we've done as well, for example, applying deep learning to archival data. And of course, we're integrated part of ESCAPE, so we help make those Virtual Observatory services available in science platforms, the Virtual Observatory software in the software repository. It's an exploratory activity about the Virtual Observatory and data lake, and that we're also trying to make sure that the VO data and services are used by citizen science and test science projects. So connecting to EOSC is a work in progress. EOSC is in development and is not set in stone. So we've followed along with the development of the EOSC. Here's a picture of the architecture of the EOSC as provided by the EOSC project itself, where we see the ESCAPE coming in as one of the clusters. And I've indicated here where some of the components map onto, for example, the Virtual Observatory services into the EOSC exchange. And then also the IVOA standards and other standards that we use having to be taken into account in the EOSC interoperability framework. Okay, so that's a very quick introduction covering a number of things. Now my colleagues are going to dive into some of the detailed topics. So I hand back to Rita to set up the next presentation.
Sure. Thank you very much, Mark, for this quick and very important intro of the overall virtual observatory, what ESCAPE is trying to do and what you are leading. So now we have, the information background. We need to understand even more better the following presentations. Now it's time to call on board Hendrik Heil. He's also from Strasbourg Astronomic Data Center, and he's going to provide more inputs about the virtual observatory. Hendrik, passing the floor to you.
Okay, so I'm going to present about what is the virtual observatory, and also to see what we are actually working on in that regard. So the virtual observatory is, in a more historical view, a comprehensive set of data and services relevant to astronomy, accessible from clients of your choice and regardless of where you are, and preserving products of digital astronomy. Historical view, because the virtual observatory is older than the FAIR principles. So we started, well, I didn't, but the people in the VO started 20 years ago to work on that and to come up with standards for interoperability. So the challenge is that you have the astronomer or the researcher on the one hand, and you have plenty of data on servers out there in something that today we could call cloud, or on servers out there, and we need to connect these two stakeholders in here. The VO is FAIR. It's FAIR means findable, accessible, interoperable, and reusable, as Mark already introduced. And I'm going to go along these modern terms for this regard when I talk about what we are doing in the VO. A lot of the VO is about defining metadata to make data findable. So in order to find data, you need to publish information about the data to a central point. You can think about that like a Google bot trying to get information about the web page to make an index about web pages out there. Something similar we do in the VO by defining metadata that a server publishes to the registry. There is not exactly one registry, actually there are 4, but they update each other at least on a daily basis. So, and we have 4 of them for backup reasons. And defining this metadata is kind of what we do. So you see, we still have the astronomer and we have the services, and these services publish to the registry, and you can find the data in the registry. The registry then allows you to ask questions like, where are images services specialized on radio data, or what services are out there dealing with time standards, and so on and so on. So we're getting more detailed there the longer we work on it, and the more new fields of astronomy come in and help us develop these standards in that direction. Namely, in the past few years, in the scope of ESCAPE and in the scope of CIVO, the radio realm, that we will listen to later in a presentation by Mario Lane, I think. Clients that are dealing with that are plenty. There are web interfaces, there's VO desktop, and actually you can use several clients to find data. Also, you can use the clients to access the data, which is sort of a different thing, because you find the data in the one hand, but to access the data, you need a protocol so you can exchange data. So it's clear, or it's obvious that you, if you want to download images, you need a slightly different protocol than when you download a table or spectra, because the clients will expect a different sort of data eventually. There are simple protocols defined in the VO. That's the simple cone search, the simple image access, or the simple spectral access, so called typed protocols, because they work in a similar manner. There is a more elaborate thing, that's TAP or ADQL. Those always come as a pair. That's the table access protocol, and ADQL is the astronomical data query language. And here the user has the possibility to make a database query SQL-like dialect to make a selection of table data somewhere. And keep in mind, table data can mean that you have a table that actually holds information, metadata of images. So you can have a collection of terabytes of images, but you make a selection based on the table data or the data that you find in the table of that, of the image collection. Mark mentioned Gaia Data Release 3 already. Yes, 1.8 billion objects in a table with 200 columns. That's something you want to use Tab and ADQL for to access if you want to make a smart move. In the VO now, let's see how that works. We have the astronomer, we have the clients implementing the VO standards. In the middle is the IDOA, which defines the standards. And these clients search the registry and then connect. The registry tells them, well, data you are interested in are on the following services. The other services don't hold these data, maybe because not at the position you're searching for, maybe not in the wavelength you're searching for, etc., etc. To make data usable, it needs to be interoperable. There's a lot about in the VO is about this, so that you do not have to follow a convention all over and the same data structure, but instead you use metadata to explain that. Standards here are the O table or the simple image access protocol, UCDs, these are unified content descriptors and more, and basically all clients do that. Also reusing data. Actually, everything in the VO is about reusing data, because published data is used for publishing and the user is using that. But explicitly, there is the protocol, the provenance tab, which is for and the data model, data model that are dedicated to provenance, so you can keep more detailed track on the data. Very short introduction. How does that work for real? So I'm going to use software to show that. This is Topcat. Topcat is a software to deal with table data, and I'm going to use the cone search protocol to make a selection. Oh, you see, I already searched for Gaia DR3 today. I will simply do it again. So you see that this is the registry search, and you see I can select several registry because there is not one entry point. In an ideal day, all of these cover the same, have the same information. And here I see, as you can see in the link here, different services that have the Gaia DR3, and I'm going to take the service Vizier basically because that's home. I searched for the Pleiades, that's Sesam, a service run by CDS, not genuinely VO, to resolve this name to this position, and I decided to go for search radius of 1.5 degrees. I run this query, and this is a data selection. So this is a data selection on almost 2 billion rows that I just downloaded 13,000 objects here. And to see how nice that works, I can make a sky plot, and you see, well, this is what my selection would look out if on the night sky, except a special thing, I didn't tell them to plot these columns. These columns were guessed by the software already. This is the position. So I didn't say, I didn't do the table names here. The information comes from the metadata provided in the VO table. So that's the answer of or the result of our query. And in the VO table, you find information called UCD, which looks like that, pos RA main. And that simply means, well, that's the main position that you should use when you want to plot something, or when you make a selection on a position. Here is the definition of these two make a position. And that is crucial because now a computer can know something about my data and can work with that. In the very easy way here, we had, well, the sky plot, and Topcat knew what that is. Interoperable, well, we have interoperability here. We use the SAM protocol. SAM protocol is designed to make two softwares talk to each other. Yes, I will hurry. Talk to each other, and I will send the data to Aladdin. Aladdin is the software that I have here. And here you see I just sent this table to Aladdin. And if I zoom in, then you see in the background the sky survey and the Pleiades are very nice. So you see the interoperability is very easy and works very well already. All these standards are defined by the IVOA. I think Mark covered that already. If you're interested in seeing that, go to IVOA.net, then you see that. And I want to finish with a slide and show you where are escape partners actually involved into this system here. And you see them, well, there are escape partners as researchers. Escape partners develop clients. Escape partners are data publishers, but was crucial for CIVU, and there's a good part of CIVU was escape partners and CIVU working on the standards so that we can have new astronomy realms in the virtual observatory. Thank you and for your attention. That's about the VO.
Okay, thank you very much, Hendrik, for this overview of the ESCAPE Virtual Observatory and how the interoperability actually it's easy here. And now it's time to go to our next speaker, which is Stefania Amodeo. She's a postdoc also at the Strasbourg Astronomical Data Center, and her presentation will be kind of a hands-on training on open science for early career astronomy researchers. So Stefania, open to you.
Yes. Hello, everybody. Thank you very much for the introduction. So I'll tell you a bit what we in ESCAPE and the Virtual Observatory are doing to train the astronomical community and especially the early career astronomers. So the EuroVO has a long tradition of schools that have been organized within a project, European project before ESCAPE, dating back to 2008 until now. And within the ESCAPE project, we've organized two schools, one in 2021 and one in 2022 this year. Both of them were online schools. And all these training events shared the same goals that were twofold. I'm listing them here. The first goal is, of course, to give the participants the unique chance to learn how to efficiently use the VO tools from the VO experts, specifically for their research. So to have something very dedicated to the development of the scientific development of the participants, but also second very important goal is for us to gather the requirements and the feedback from the participants so that we can improve our tools for the different communities and also to improve in the way we organize hands-on sessions and training events. So this is a very condensed program of our schools that we've named Science with Interoperable Data, and Hendrik has explained you what this means for the virtual observatory. So in our school, we've introduced the participant to the vision of ESCAPE and of the European Open Science Cloud, and we've presented them a number of tools and services of the virtual observatory. Some of them have been introduced by Hendrik before, but what has proven to be useful and interesting for the participant is to see these VO tools in action on real life scientific applications. I'll show you in a bit some example of this. So we organized the schools so that after this hands-on session, there was 1 week of asynchronous work on the participants project, where each participant had 1 or 2 tutors associated based on their interest. so on their proposed science and interest in a specific data set. So we valued a lot this close interaction between the participant and the tutor, because this is proven to be very useful for the student, and it has been very rewarding to see at the end of the school the presentation from the participants, and to see their work effectively on a specific on their own science case. And then we've collected the feedback and all the material. What's also very important is that all the material for the school is available online. So for future record, for more students that are interested in VO, it is possible, and it's very easy to access this material. I'm giving now you some more details about the latest school that we have, and then I'll give you the link to both schools. So this was held this year in February 2022. And it was online. So as you see, we tackled some tools that we hosted the CDS, but also had some in collaboration with the Spanish VO, very nice tutorial on the transient event exploration, the use of Gaia data, so very large catalog. We also introduced tutorials using Jupyter Notebook. So how to use the virtual observatory tools within Python script. That's something that the young community starts to really appreciate. And the ADQL language to access big data sets, and also very interesting tutorial on the electromagnetic follow-up of gravitational waves events. So this is a picture of our participants. So in our school, we had on average between 30 and 40 participants. This is to ensure that the level of discussion and interaction is good, and of course that we can maintain it, especially with online schools. And the participants had research interested in literally any field of astronomy. There were mainly early careers, so mainly PhD students or young postdocs. And also master students. We hosted also a few senior scientists, and coming from most of them from Europe, but the online event also allowed some participation from outside Europe. So this is what I was mentioning, the participants project. You can also find the slides and the links, the useful links for the for these presentations in the link that I'm providing here. And I'll finish with the group photo from our first and second school, and you will find the links at all the material available following this this slide here. And I'll stop here. Thank you.
Thank you very much for this presentation. And now it's time to go to our next speaker, Marjolein Verkolter. I hope I said properly. She's
Very
from
properly.
Jive, and sorry?
Very properly, thank you.
Thank you. So now we are going to let's say, to the second part of the webinar. So we had kind of an intro about the Virtual Observatory, and now we are going to do the following speakers will provide some insights on how the Virtual Observatory has been helping their own institutions, and we are going to start with Jive, where Marjolaine is part of. Marjolaine, it's your turn.
Okay, let me share my screen. I hope you can see my slide now and you can hear me.
Yeah.
Okay, good. Thursday, the 24th of March, 2022 marked a very special occasion, even though that was not reflected in that day's headlines. What happened that day is that if you ran this little Python script looking for the oldest data in all of the radio catalogs that the Virtual Observatory knows of, you would, amongst the results, suddenly see this result appearing. This wouldn't have happened the day before. So the archive of the European VLBI network was officially connected to the Virtual Observatory. Now, why was this a special occasion? Well, for that, we need to go back a bit in time. Back in the 2006-2007 timeframe, the EC-funded Astrophysical Virtual Observatory project was finishing and followed up by the EuroVO project. Integration of radio data into the VO was already a topic then, and more specifically, the difficulties with interferometric radio data. So my name is Marjolein Verkouten, and I work at the Joint Institute for Very Long Baseline Interferometry. And I'm here to tell you about why VLBI data doesn't easily fit into the VO and how ESCAPE helped. So as it turns out, the largest steerable structures that can usually be built are dishes of about 100-meter diameter, such as this famous one in Germany. However, its resolution may come as a surprise, because at radio wavelengths, this telescope can only see details as small as the full moon, which means that it has only a handful of pixels across the M31 galaxy. So for smaller telescopes, it's even worse. Now, fortunately, there's a solution. Instead of building one large telescope, it is also possible to build two smaller ones, place them 100 meters apart, and combine their signals in a process called correlation. The resulting data set provides the same resolution as the original 100-meter telescope. But if you decouple the telescopes anyway, why stop at 100 meters? So the European VLBI network uses this concept to build a virtual radio telescope and uses a loose definition of Europe. It includes sites in South Africa, China, Korea, and its longest baselines simulate a telescope of 8,000 kilometer diameter. And it is Jive who performs the correlation for the European VLBI network and hosts its archive since about the year 2000. Now, if you look into the archive, the real difficulty actually starts there, because many astronomical instruments produce images. But radio interferometry measures amplitudes and phases of the two-dimensional Fourier transform of the image domain. As such, the EVN archive does not actually contain images. It contains amplitudes and phases as a function of time. Now, a VLBI image is built up over several hours, and the changing Earth's atmosphere and ionosphere introduce errors in the signal over time. In fact, VLBI sources are so weak that we need to cycle between target and strong calibrator to be able to correct for those errors. Now, without specific post-processing, the science target will never be seen. And I'll leave it up to your imagination to guess which of these two sources is the calibrator and which one is the weak target source. Another hurdle is that the inversion back from visibility data in the archive to an image is not unique. Those parameters are user tunable and allow processing for a specific science case. So in the VO search results displayed earlier, this is also reflected in the calibration level. The EVN data is not science ready. The correlated data is stored in so-called FITS-IDI files, a format for radio interferometry data. But the archive contains a lot more. It contains calibration and flagging data, as well as pipeline and inspection images, none of which are science ready. So considering all that, this might be a valid question. As it turns out, with a telescope the size of the Earth, you can do interesting things. It's possible, for example, to follow matter being ejected by an active galactic nucleus at a redshift of 0.4. Fast radio bursts can be localized within their host galaxies, or you can start to image black hole event horizons. Now, specifically, the use cases for Virtual Observatory are these: finding historic data, the possibility to reprocess the data, and providing standardized access methods to the archive data products. So for the EVN archive, two IVOA protocol standards do apply: the one to find the data and the one to link related data to the search results. ESCAPE Work Package 4 facilitated JIVE to participate in the IVOA Radio Special Interest Group to work on supporting visibility data in the OBSCOR standard. For example, to work on experimental characterization of the visibility plane in two numbers, ellipticity, filling factor, and this was work done together with Astron. The Work Package 4 further enabled the creation of the OBSTAP service by providing funding for hardware and resources to write software to extract the OBSCOR parameters from the datasets in the EVN archive. So the net result is that it is now possible to perform an ADQL query on the EVN archive. And for a given search result, data link entries to the raw data and calibration data from the archive are findable. So clicking on FITS IDI results in this, which is a content that experienced astronomers will immediately recognize as FITS. But ESCAPE did a lot more. Through funding in Work Package 3, JIVE could work on improving VLBI data reduction software and provide a Jupyter kernel for notebook-based processing. And in Work Package 5, JIVE was able to purchase a JupyterHub server and work on developing plugins for that system. So putting all this together, it is now possible to visit jupyterhub.jive.eu, log in with your ESCAPE credentials, start the EVN archive plugin, perform a com search, which behind the scenes uses the VO query interface. And then for a search result, it is possible to open a Jupyter notebook dedicated to the processing of that specific search result. And specifically, the download of raw data and calibration information goes through the VO data link protocol. So this has the benefit of significantly lowering the barrier for VLBI data processing. And finally, I would like to leave you with this. With the EVN archive accessible through the VO, it is possible to find all observations since the year 2000 archived in JIVE, and they're here visualized in Aladdin. And this, I would like to say a huge thank you to ESCAPE and Work Package 4. Thank you.
Thank you very much. Now we are going to have ESO's story, and for that we have Martino Romaniello, who is part of ESO, and he also is a ProjectScape member. So Martino, over to you.
Hello, hi, good afternoon. There is some construction work on the background, which I hope will grace us for the next 8 minutes. If not, apologies for that. There's somebody tearing down a wall behind my back. So, but apart from that, let me share my screen. And there we go. Okay, bang. And now with some luck, you should be seeing my presentation full screen. So, yes, as Rita said, I'm Martino Romaniello. I've been an astronomer with ESO for, well, longer than I care to remember by now. And I'm heading a unit that's called Backend Operations Department. And behind this slightly mysterious name, what it means is that we deal with the science data as it leaves the observatory. Because after all, this is what we're talking about. So who are we? So ESO is the European Southern Observatory. So, and what we do is that we develop ground-based astronomical telescopes and observatories, and we operate them to secure that the science community has access to the high-quality data that it generates. ESO was founded exactly 60 years ago this October, so happy birthday to us in a sense. and it's funded by 16 member states. Our telescopes are in Chile. This is the picture on the bottom right, and our headquarters are in Garching in Germany, so close to Munich. And the reason why telescopes are in Chile is that because Munich is a lovely place to live, but not necessarily to look at the sky if you're not interested in clouds, but if you're actually interested in the astronomy part of that. So that's why telescopes are there. And we operate there a series of facilities that cover the wavelength range between near ultraviolet, optical, all the way with ALMA to a millimeter, to sub-millimeter and millimeter. So this is who we are. And where does the data fit in all of this? So where it fits is that they are really front and center on what we do. So what we do, and this is from a very high level policy document blessed by Council, which is the highest governing body of ESO. So this is very high level. So what we do is that we operate telescope to optimize scientific excellence. That's, you know, a great motherhood statement. But I would like to draw your attention to the bold part here. So telescopes are operated within an end-to-end process. This is all embedded how we operate, which ends with data preservation and publication. So the goal of all of this is to generate data, and by supporting open data policy, making this data available for scientists worldwide. The archive, so making data available to users, is a huge driver for the science output of ESO. One way to illustrate this, there are more, but you know, this is one of those, a particularly poignant one, is to ask oneself, what is the percentage of all of the output of ESO science measured in publication, so in refereed publication, what is the fraction of this that couldn't have been done without having an archive with open access to the data? And you can see this is a time series, so it starts from 1999, it goes up to today, 2022. And you can see that this has been steadily increasing, and by now about 35 to 40% of all of the science output of ESO is attributable to the archive, so an open use of the data. The impact of the science archive beyond just the counting publication is rather large. First of all, it allows to scrutinize every science result, and this is really a staple of the scientific method. Everybody can go back to the data and challenge any result that somebody else has claimed. Then it fosters a culture of cooperation and open data in astronomy and science in general. And in general, astronomy has been quite active in leading this. And it broadens the ESO community beyond its traditional niche. It's a large community. It's interesting to note that 1/3 of the archive users are new to ESO. So there are people who only access ESO through its data. The archive reaches more early career scientists than traditional users, which is again a great way to broaden the community. And it reaches beyond the member states. So the member states are the 16 ones that I mentioned at the beginning who fund us, but data is open to everybody, absolutely everybody, beyond any boundary. And it is a great thing that open science does. So where does the virtual observatory fit in all of this? The VO is absolutely crucial. If you think that about 50% of the ESO science results use data from more than ESO itself, this already tells you why sharing data is so crucial. And the virtual observatory is the de facto standard to do that. It provides the standards, the protocols, the tools to make interoperability, as we call it with a slightly technical jargon. This is what virtual observatory enables sharing the data and getting to the science results. And all of these, the standard, the protocol, the tools, need to evolve constantly. And this is really a great contribution that CIVO did. So the ESCAPE work package for CIVO that it brought to the larger picture of making science in this modern world. And this is for the ESO data itself and to connect it globally. In fact, whatever you do with ESO data, whether you know it or not, uses the virtual observatory. Here I'm listing just, it's a phone directory, if you will, of some, not all, of the VO products that we use in the archive. Some of them are directly exposed to users, some of them are for our internal use. All of it was developed by the VO, and CIVO is crucial for that. So whatever you do in using ESO data, you will be using the VO. This is just a graphical illustration of some of this, and these are different archives. At the top, our archive, the one in the center bottom is an ESA's archive, but they all illustrate interoperability of data enabled by the VO. Top left, this is ESO data interconnected with gravitational wave data. So if you want to find your optical counterpart to a gravitational wave source, that's the way to go. You can do that. Center here is ESO plus HST data, and this is all the connection is made through VO. The data is not even in the same place, and this is all connected through the VO, through the registries that Mark was hinting at the beginning. And then to the right, this is ESO connecting La Silla Paranal data, so optical and infrared, to ALMA data, again through the VO. To summarize in my last 30 seconds, ESO and CIVO. The virtual observatory is central to the success of the ESO Science Archive. We couldn't do without. CIVO provided crucial support to the ESO Science Archive at several levels. This continued support for development of tools, protocol, and standard, which is needed because data evolve, science cases evolve, and the VO needs to evolve with it, and CIVO provides for that. It involves the astronomical community and expands the astronomical community, and it connects the ESO data, the astronomy data, to the wider context of the EOSC, so the European Open Science Cloud, which is a common framework for European open science. And with this, I thank you very much, and I'll stop here. Thanks.
Thank you very much, Martino. Luckily, your presentation was very smooth, and the noise you were mentioning about did not bother.
But you did hear it. Sorry about that.
They did not bother, so no worries. It's totally fine.
Okay, great.
Thanks, Martino. And now it's time to go back to where he started. So I'm passing the word to Mark again for the closure of all these presentations.
Okay, thank you very much, Rita. So hopefully we're not just back where we started, maybe the same person.
The same person, the same person.
So yeah, it's my pleasure to sort of, after having these really nice presentations by the partners in the project, we've chosen, Jive and ESO as the specific partners to tell us about the effect of participating in ESCAPE. CIVO has had on their research infrastructures, and really pleased about that, and of course about their enormous contribution into the project as well. I mean, remembering the approach of bringing those different sorts of partners together, I think that's really the key to making these things work. So I'm going to quickly go over some of the achievements and the outlook of the work that we've done in ESCAPE and beyond. So I showed you the approach before, and this is kind of some of the results that have come from that. We've, in terms of integrating the virtual observatory services with the EOSC, we've written analysis reports about how that works, and hopefully that is really interesting to the EOSC and to the EOSC Future project and to the architectures of the EOSC itself, because this is how a domain is trying to connect to EOSC and what the benefits and what the problems are. In terms of developing our standards, you've heard a lot about those. That's been a large part of the work. All of those little pink tags in this thing are milestone reports of the ESCAPE project and deliverables. Stefania and the group of people who have helped the young people to use the services, thank you very much. That's been really amazing to have the difficult situation of being online for almost the whole project, but still managing to enable those young people to make new results and new tools based on the services. We also have Stefania emphasized the reusability of the tutorials for the schools, but we also have tutorials and information and documented cases for hands-on works that came from hands-on workshops about making the data providers, enabling the data providers themselves to publish to the VO. And of course, we've had a few fun and really interesting results that have come from, for example, providing value-added services on top of those archives. So here's another architecture diagram, at this time of the virtual observatory. All of the pink dots are the places that we've been able to help our infrastructure partners contribute in. I have another, this is that I'm really proud about in the project. For each one of the ESFRIs and research infrastructures that are involved in ESCAPE, CIVO, you know, we have helped them become actors in actually making the standards and using their feedback and priorities for how those standards are developed at the international level. So for ESO, Martino's highlighted the VO standards in the archive. For the gravitational waves, we've developed a new spatial temporal indexing system that enables interoperability in both space and time, and we have a nice published paper about that. For Jive, thank you, Marilyn, as well as partners from the Square Kilometre Array and ALMA and LOFA, we've helped make a whole new radio astronomy group at the IVOA and new services that provide radio astronomy data. So Jive is one of them, thank you very much. But there are also others from LOFA and other, and from Astron. For the for high energy astrophysics in the Cherenkov telescope array and the KM3 net neutrino detector, we have used their priorities to build provenance standards that have now been approved by the IVOA. There have been workshops on how to implement those. There have been papers published. And I think that's another very successful activity that's responded to the needs of those infrastructures for the components for open science. And for our solar partners, who are at a much earlier stage of sharing data, we have helped them to develop virtual observatory metadata for solar physics, and also to bring online some of the first table access protocol services for solar data. Here are a couple of examples of those standards that have been approved at the international level based on work that's been supported by ESCAPE. One is the IVOA provenance data model. The other one is called the multi-order coverage map. And those are all a bit cryptic until you start to use them. The IVOA, it's the metadata that allows us to deal with all of those gravitational wave probability distributions on the sky that you see here, using that standard way of doing it. We've highlighted the results, for example, about the improvements to data discoverability in the archives. And we highlighted, of course, a lot with the press release, the multi-messenger observations using that mock multi-order coverage map standard. So in terms of connecting the virtual observatory to the EOSC, we've made some progress, but I would say it's not enough. And it's not enough in that to see the virtual observatory services in the EOSC portal, you have to know that they are in beta find. And if there's anybody listening out there, that's what we really want to make happen, because we have imported the whole catalog of a discipline of astronomy, the Virtual Observatory Registry, into beta find as a stepping stone into the EOSC. And that's worked really well. You can see that there are more than 22,000 data sets available in that standardized metadata that allows that catalog to be visible. And there's just a small stepping stone for that to be able to be, since beta find is already in the EOSC catalog, but there needs to be greater visibility of those data that we've already onboarded. Okay, so you can see some of the services that are related to astronomy in there. And then as a closing, I'd like to show you something very visual, because we've also pushed a lot on the improvement of the core interoperability components that get installed in, for example, the ESO archive, different partner institutes for visualizing their data. And this is a new improvement of what's called Aladdin Light version 3, which uses those standards. Thousands of data sets, just about a new version that is much smoother, that allows different sorts of projections. So you archive eventually, and for the tools that the astronomers are using. So that little video just showed you some of the manipulations that you can make with the different projections that weren't available before. And so it's been a priority for many of the ESFRIs, and these are sort of pre-release snapshots of what's coming. Hopefully it's whetting your appetite for that. And in terms of the radio astronomy data, one of the pathfinders for the Square Kilometre Array is the telescope in South Africa, and they have released a really beautiful image of the galactic center. And so we've been able to include that into our, and it has the same sort of interoperability. You can zoom into the data where you're accessing higher and higher visualization versions of it. And in this new version of the visualizer, you can change the dynamic range. There's a lot more scientific capabilities inside of it. Okay, so, and that's being used into the SKA prototyping visualization activities. So last slide, the future of the VO in ESCAPE and in EOSC. Okay, we've made the first integration of astronomy VO data services into the EOSC. EOSC is evolving very quickly. The next big step for that, after the basic onboarding, is to use the enhanced EOSC resource catalog, which enables a more direct onboarding for data sources. So that comes very late in the project of ESCAPE. So it has to be pushed. That is something that can happen a little bit at the end of the project of ESCAPE, but is really a view to the future. In terms of the standardization and doing the enabling open science at our research infrastructure partners, you've seen the examples today of ESO and JIVE. There are the other examples of the other partners, and the future of that is more implementation. There's an essential level of coordination that Martino mentioned. You can't really do it. Any one institute just can't do that by themselves. There's an innovation and there's a scaling up. So there's a continued networked approach that we really need to make sure that the standards are in place, the data are available, the tools and services, and the essential training continues to happen and to bring on the new things. In terms of the whole ESCAPE vision, we have the integration of this within its platforms and research, virtual research environments. And it goes beyond that because we have the space agencies and other major observatories around the world that are using these components as well. So thank you very much to everyone who listened today and to all of the other participants who have presented and everyone else who has contributed to our work package and to ESCAPE in general. So with that, I thank you very much and we'll be open for questions.
Hi, Mark, thank you very much. And in fact, we have 2 questions. I know it's already a little bit past 4, but I believe we can spend a couple of minutes to address the question. So the first one we received is from Pierre, and I believe Marie-Hélène will be the person to reply to this one. So for those who are here, the question is, it's nice to be able to discover radio interferometry data through Aladdin. Once found Aladdin purposes several products to download. The question is Aladdin able to make sense of the downloaded FITS files? I assume it does not. Then, is there any existing plugin that will generate images from the visibility files, or at least a rough preview? Or is that too complex and reachable, and the visualization must be done on?
Okay, yeah, it's a very interesting question.
Maybe this is what we have.
I don't hear the.
We can hear you, Marie-Hélène.
Okay, so no, the simple answer is no. There is the visibility data is pretty large. A very small data set is 500 megabytes or so. But more specifically, like I indicated, the science targets, they're very, very weak, and without very adequate calibration, you don't see them. What we do in our archive, and because of the shortness of the 8-minute presentation, I didn't explain, but in our archive, there are, we do run a standard pipeline on the calibration sources, and we provide uncalibrated previews, and those calibrators you can see, but and our idea is that in they will be connected to the search results through the data link protocol as a preview image. For the science targets, we really cannot do that because the original scientist really has to do a proper calibration. Having said that, our goal is to have in our archive the ability to feed back publications and references to published results from a data set, such that if you find the raw visibility data in our archive, that you can immediately find, again through the data link metadata, that you can find derived results like people that have imaged the science targets. And maybe that is sort of the easiest way around this, because doing it yourself is pretty difficult.
Okay, thank you, Marlene. And I believe there was another question from Carsten about the EOSC, where, for example, on the Carsten is involved in the SHOCK project, and they are facing some issues with connecting with the EOSC. And Mark already provided some inputs on the written chat, saying that in case of Scape, the Scape is interacting with the ODAP project to onboard the whole Virtual Observatory catalog into the EOSC. Mark, I'm not sure if you'd like to add something else. Otherwise, I think we can close this webinar.
I think we can close it. I just thank Carsten for reaching out, because we're talking to some of the other cluster projects like Escape, but in other fields. There's PanOSC, there's ENVRI Live, there's EOSC, there's ENVRI Fair, there's EOSC Live, PanOSC, and I think we are, as scientific projects, we're having some challenges to get what we need done into the EOSC portal. So I take your contact, and I think we should discuss more about that.
Okay. So I think the webinar is over. So I would like to thank all the speakers who are involved here, and also the Scape communication team who brought this webinar into this, and of course to all those who registered and were here with us. Thank you for listening, and also thank you for your questions. You have our social media channels on Twitter or LinkedIn. They are listed on the chat. And as a reminder, this webinar recording and all the presentation will be available for download on the webinar page in the next days. Once again, thank you very much. Have a lovely Thursday and keep in touch.